overall, an outline of what we'll be talking about today. Part one, as I mentioned, I will be presenting on the SEAOC efforts and these what's been called SEAOC PV1 guidelines for seismic design of unattached arrays. And in part two, Andreas will jump into some of the technical details and really the cool analysis and testing that led to the practice right now and these SEAOC recommendations. So for part one, I'll first just look at a number of different types of solar arrays and hone in on which ones we are addressing here. We'll talk about earthquake effects on solar arrays and then the details of the SEAOC PV1 guidelines. Two of the sections that we're going to highlight in particular there are how you determine and what you do with design displacement, seismic design displacement, and then also a topic of seismic interconnection that holds an array together throughout an earthquake. Solar arrays. I'm going to show a number of images of solar arrays here. This is one example of what we call a solar array out in the desert. This is a ground-mounted, relatively small array. Also called a solar array is this much larger array or happens to be located on top of a roof of a reservoir. Panels are much closer to the surface of the roof in this case. This is also a solar array, a ground-mounted tracking system where the panels are high overhead in a parking lot and they move over the course of the day. And there are a number of other types of solar arrays. So flat roof commercial systems, sloped roof flush mount systems, other solar carports and structures on top of parking garages, ground mount systems. There are a number of things that are called solar arrays, and the point of showing these slides is just to say that we are talking about one particular type today, and one of the challenges in developing guidelines for design is to define the scope of what you're addressing. So what the SEAOC PV1 guidelines address is large flat roof, or I guess they don't necessarily have to be large, but flat roof installations such as this one, where you've got panels that are close to the roof surface. They are located on top of a building, and it's a low profile array. And one reason for what started the SEAOC committee down this path was a number of questions that were coming from the industry about how to address these types of arrays, because they were a big segment of the industry placing solar arrays on top of otherwise unused space that was soaking up a lot of sun near where the power is needed. So it presents an opportunity. It also presents a challenge because it means in a lot of cases working with existing buildings that weren't originally designed with solar arrays in mind. So that means you're dealing with existing roof surfaces, existing framing, and trying to interface with that in design of your solar array. To meet that opportunity, one approach that is helpful or sort of limits some of the interferences you have to deal with in dealing with an existing structure is to work with unattached arrays. So unattached arrays, here we use that term to mean an array that's not physically or structurally connected to the roof structure. It has some advantages or reasons why people are interested in doing this, and the primary one is that it means you're not penetrating the roofing membrane. Roofing membrane penetrations create costs in terms of flashing and potential for leaks, and also limits your flexibility in terms of future modifications by installing that sort of modification to the structure. So unattached arrays then raises a certain number of questions. It means that you're avoiding having to create attachments to the roof structure, but it also means that the array can slide in an earthquake, and you have to be able to accommodate that. To accommodate those displacements, you need to provide seismic separation from the roof edge and other objects, and essentially the SEAOC PV committee was formed to answer this question: how do you go about doing that?